The 6 carbon atoms in the middle are approximately the equator of your globe. Welcome, OChemNinjas. In this video, I want to introduce you to the chair structure and show you some of the terms and definitions that chemists use in this field. To begin, let's build a model of cyclohexane. Go ahead, grab a model kit, and build C₆H₁₂. The colors here are just meant to be placeholders. They're not meant to represent other elements like nitrogen or oxygen or fluorine. But build the model with 6 carbons in the center, 2 of them being blue, and 12 hydrogens on the outside, with a couple of them being red, a couple of them being green, and the rest of them can be the regular white hydrogen. If you pay attention to the wedges and dashes that I have here, it will make the transition to chair structures a little bit easier. Here is my version of this molecule. I like this model kit. It's one of my favorite model kits. If you'd like to learn more about this model kit, I have a link to information about it in the description down below. The first thing to say about this line angle structure of C₆H₁₂ is that it looks like all 6 of those central carbons are all coplanar. And you can make them all coplanar. It actually takes a little bit of work to get all 6 carbons to be coplanar. The bonds really don't want to bend this way. And that's because this is a very unstable version of C₆H₁₂. When you take this version of C₆H₁₂ and you look down any of the 2 bonds, you can see that all of the hydrogens are all eclipsed to each other. No matter how you rotate the molecule, those hydrogens on neighboring carbons are always eclipsed to each other. That makes this a very unstable version of C₆H₁₂. Now, there is a place for this planar version of C₆H₁₂. We see it often in biochemistry. Just like the Fischer projection, biochemists like to use the least stable conformation of molecules as their preferred perspective orientation. When we draw the ring this way, it's called a Haworth projection. The Haworth projection assumes that we're looking at the ring side on. When we look at the ring side on, these 2 carbons are closer to you as the viewer, and that is implied in the Haworth projection. These 2 carbons on the bottom are implied to be closer to you as the viewer, and this entire bond is closer to you as the viewer. These 2 carbons that we draw on top are assumed to be further away from you as the viewer. In a Haworth projection, we draw in the hydrogens as vertical lines from each carbon. Our biochemist friends use the Haworth projection to differentiate between the cyclic versions of the various sugars. We really won't see them very often in organic chemistry. Instead, let's reorient our cyclohexane so that it is in the most stable conformation. To do that, we'll use the 2 carbons that I've labeled blue. These are going to be our anchor points as we go through this analysis. With the cyclohexane oriented with the blue carbons on either side, take the blue carbon on the left and rotate it up, and take the blue carbon on the right and rotate it down. We could have gone the other direction with the carbon on the left down and the carbon on the right up. In fact, you can go back and forth between these 2 versions. It's really easy to do with this model kit. That's one of the reasons why I like this model kit. But I'm going to choose the carbon on the left pointed up and the carbon on the right pointed down. That is going to put our molecule into the chair structure. The chair structure is the most stable version of cyclohexane. As we look down all of the bonds this time, all of the hydrogens are completely staggered to each other. That makes it the most stable version of cyclohexane. When we draw this cyclohexane, we will draw it in its chair conformation. This isn't a video about how to draw these chair structures. I have a separate video on that I'll link to down below. Right now, we're just introducing the topic, going over the terms and definitions. If you're looking for the chair structure in this version here, it would be right around here. Those blue carbons, the ones we rotated up and down, are going to be the carbons off to the far left and off to the far right. One of the analogies that's really useful for thinking about the chair structure is to kind of start thinking about it as a globe. You can kind of see a sphere kind of encompassing all of these atoms. The 6 carbon atoms in the middle are approximately the equator of your globe. Some of the groups stick up above and in the northern hemisphere, and some of them stick down into the southern hemisphere of this globe. The 6 carbons around the equator include our 2 blue carbons, the ones that we rotated up and down, and these are my anchor points when we draw our chair structures. I call them my corner carbons. That's my term, I came up with it, but it helps us orient when we're talking about chair structures. We can always find the carbon furthest to the left and the one furthest to the right. Those will always be our corner carbons. Sometimes they're pointed up, sometimes they're pointed down. Sometimes we can flip them around like we did earlier. If you can get comfortable with flipping these corner carbons up and down and knowing what that means, then that will really help us later when we talk about chair flips. As we go to add in the rest of the groups, notice that some of these groups stick straight up and straight down. The red hydrogen on the corner carbon on the left sticks straight up, and the red hydrogen on the carbon on the right sticks straight down. As we go to add the rest of the groups around the ring, let's make note of the 3-dimensionality of the chair structure. Just like the Haworth projection, these 2 carbons on the bottom are assumed to be closer to you as the viewer, and these 2 carbons up top are assumed to be further away from you as the viewer. That completes the globe-type orientation of these 6 carbons around the equator. As we go to add the green hydrogens, notice that they are also all sticking straight up or straight down, and notice that whether it sticks straight up or straight down changes every other carbon. For the corner carbon on the right, the red hydrogen was sticking straight down. For the next carbon over in the front, the green hydrogen will be sticking straight up. The green hydrogen on the carbon in the front next door will be sticking straight down. The red hydrogen is pointed straight up, and the green hydrogen on the carbon in the back is pointed straight down. Watch what I do to indicate that this is in the back. When I go to draw that bond, I'll break the stick a little bit and then draw the rest of the stick to show that it is behind that orange bond in the front. I did not do that with this green hydrogen because it really is in front of this back orange bond, so it is a straight line straight through that orange bond to show that it's in front. The last hydrogen is a green hydrogen in the back that's sticking straight up. So for all 6 positions, we have a bond pointed straight up and a bond pointed straight down. These are all axially parallel to each other, and so we call these the axial groups. We're now ready to add in the last 6 groups, and they are all around the equator of our globe. They're not really parallel to each other, but they all kind of stick out around the equator, and we call them equatorial groups. Notice something interesting about those equatorial groups. On, let's say, the right carbon, where the axial hydrogen was pointed straight down, the equatorial hydrogen is pointed up into the northern hemisphere just slightly. The axial hydrogen is pointed down into the southern hemisphere. The equatorial hydrogen is pointed up into the northern hemisphere just slightly. It's still around the equator, but it is pointed up into the northern hemisphere. The same is true for the yellow equatorial hydrogen on the blue corner carbon on the left. The red axial hydrogen is pointed straight up, so the equatorial hydrogen is going to be pointed slightly down into the southern hemisphere on that carbon. The same will be true for the 4 hydrogens in the center. If the axial group is down, the equatorial hydrogen will be slightly up. If the axial hydrogen is up, the equatorial hydrogen will be slightly down. The question is, do we draw that equatorial hydrogen to the left or the right of the axial bond? By convention, we draw the equatorial hydrogen to point towards the corner carbon it's closest to. So for this carbon in front, the closest corner carbon is here to the left, so we would draw the equatorial carbon up into the northern hemisphere and towards that corner carbon on the left. The same is true for this back carbon here. The closest corner carbon is the one to the left, so we would draw the equatorial carbon slightly into the northern hemisphere and pointed towards that corner carbon to the left. For these 2 carbons on the right, the closest corner carbon is to the right, so the equatorial hydrogens will point to that corner carbon on the right. Since both of these axial hydrogens are pointed up into the northern hemisphere, both of these equatorial hydrogens would point down into the southern hemisphere towards that corner carbon on the right. And that completes the chair structure for this molecule. When we talk about chair structures in the future, we'll use these terms like axial and equatorial. I'll use the terms corner carbon, even though that's not really a term, and we'll use these to talk about how we orient the chair structure and what the different parts of the chair structure mean. I want to leave you with one important point. We saw that some of these groups were up in the northern hemisphere, some were in the southern hemisphere. We also saw that some of these groups were axial groups and some of these groups were equatorial groups. They are not linked. One of the big misconceptions I see in this unit is students think, well, if it's in the northern hemisphere, it must be an axial group or something like that. If we just look at the 2 corner carbons, this red hydrogen on the corner carbon on the left was on a wedged bond, so it's up in the northern hemisphere, and that happens to be an axial group in this carbon. But in that corner carbon on the right, the axial group was on a dashed bond, and it happened to be in the southern hemisphere. So just between our anchoring carbons, we can see that sometimes the axial is in the northern hemisphere, sometimes it's in the southern hemisphere. Same is true with the equatorial. Sometimes the equatorial group is in the southern hemisphere, sometimes the equatorial group is in the northern hemisphere. So we can't make any type of association between the wedge dash notation and the line angle structure and whether it will be axial or equatorial in the chair structure. The one guiding principle I can give you is to look at the carbon from which you're sprouting the bonds. If that carbon happens to be pointed up, like this corner carbon on the left happens to be pointed up, the axial group will also be up. If that carbon happens to be pointed down, like this carbon in the front is kind of pointed down, then the axial group will also be pointed down. That alternates every other carbon. The axial group will be up or down in the northern or southern hemisphere, and the equatorial group will follow suit. With this as a foundation for chair structures, you're ready to be a chair structure ninja.
Thanks for joining us today, ninjas. Be sure to watch these other videos to level up your ninja training even more. As always, don't forget to like and subscribe.